Okay, friends, today we are going to see cyclic quadrilaterals. Okay, Euclidean geometry, part 7 of 25. Okay, what is a cyclic quadrilateral? A cyclic quadrilateral is a quadrilateral around which a circle can be drawn to pass through all of its vertices. Okay, vertices are corners. So, not all quadrilaterals are cyclic quadrilaterals. Okay, example of a cyclic quadrilateral. You have this quadrilateral. You can see a circle can be drawn to pass through all of its vertices. Okay, all of its vertices, all the corners. Okay, the circle can pass through all the corners of this quadrilateral. Now, proving a cyclic quadrilateral. How can we prove that a quadrilateral is cyclic without drawing a circle around it? In Euclidean geometry, we have three ways to prove that a quadrilateral is cyclic. 1. For a cyclic quadrilateral, the opposite angles add up to 180 degrees. And 2. For a cyclic quadrilateral, exterior angle is equal to interior opposite angle. And 3. For a cyclic quadrilateral, angles in the same segment subtended by the same chord or same arc are equal. Okay, we have three ways to prove that a quadrilateral is cyclic in Euclidean geometry. Okay, let's start with the first one. Okay, the first one. For a cyclic quadrilateral, the opposite angles add up to 180 degrees. Okay, let's see an example. You can see the angle B and the angle D are opposite angles, or the angle A and the angle C are opposite angles. This angle and this angle are opposite. Okay, angle B and the angle D, if their sum is equal to 180 degrees, in this example, you have 79 plus 101. Okay, 79 plus 101. This is equal to 180 degrees. When you have this situation, therefore, ABCD is a cyclic quadrilateral. It means a circle can be drawn around this quad in such a way that all four vertices are going to be touched. My circle is not that good, but I hope you understand what I'm trying to do. Okay, or angle A plus angle C. The two angles are opposite. Okay, if angle A plus angle C is equal to 180 degrees, in this example, you have 92 plus 88. Okay, 92 plus 88. This is equal to 180 degrees. When you have this situation, therefore, ABCD is a cyclic quadrilateral. It means a circle can be drawn around this quadrilateral in such a way all these four vertices are going to be touched. Okay, so you just have to prove the sum of one pair of opposite angles is equal to 180 degrees. Okay, one pair is enough. Do not do this and this. Okay, number 2. For a cyclic quadrilateral, exterior angle is equal to interior opposite angle. Okay, let's see. Okay, this is an exterior angle, meaning outside. If this angle, let's call it theta, if the angle theta is equal to the interior opposite, okay, this is the interior opposite, not this, not this. This is adjacent to this. This is adjacent to this. This is opposite. Okay, adjacent means next to. If this angle is equal to this, okay, if theta, the exterior angle, is equal to the interior opposite angle, which is A, then ABCD is a cyclic quadrilateral. Okay, you can also use this exterior angle. The angle, let's call it beta. If the angle beta, which is an exterior angle, is equal to this angle, okay, interior opposite angle, this angle, okay, if the angle beta is equal to the angle D, therefore ABCD is a cyclic quadrilateral, okay. So again, you just have to prove that one pair of angles are equal. Now the third way to prove that a quadrilateral is cyclic. Okay, for a cyclic quadrilateral, angles in the same segment subtended by the same chord or the same arc are equal. Okay, if the angles are equal, then you have a cyclic quadrilateral. So you are going to look for the bow tie shape or butterfly shape. You have this, a quadrilateral. How can you prove that this quadrilateral is cyclic? So, can you see? You can get a bow tie shape or butterfly shape. Can you see this? This is some sort of bow tie shape or butterfly shape. Whenever you have lines crossing inside a quadrilateral, you have to think of the third way. So this is how you are going to go about proving this quadrilateral to be cyclic. Okay, let me erase this. You can use any side. Okay, any side. The sides are going to be your chords if you have a circle drawn around. If we use this side, DE, okay, using DE, this side, okay, if you use this side, now you have to prove that this angle and this angle, okay, this angle and this angle. You can see the two angles are subtended by this side, DE. Okay, you have this line coming from there, going there, and you have this line coming from there, going there, and you have this line coming from there, going there, you have this line coming from there, going there. Okay, you can see the two angles are subtended by the same chord. Okay, this would be a chord if you have a circle drawn around. This will be a chord. So if you can prove that this angle is equal to this angle, then this is a cyclic quad. If this angle is equal to this angle, okay, using this side, you have this angle and this angle. If the two angles are equal, then this is a cyclic quad. Okay, I can erase this. So, if the angle, this one, DGE, okay, is equal to the angle DFE. If the two angles are equal, therefore DEFG is a cyclic quadrilateral. You can also use this side, using the side EF. Now, if you use EF, you are going to prove, let me show you. If you are using EF, okay, EF, you are going to prove that this angle, and this angle, if the two angles are equal, then this is a cyclic quadrilateral. Okay, you can see the two angles are subtended by the same side, the side EF. or the same chord. If you have a circle drawn around touching all four corners, this is going to be your chord. If this angle is equal to this angle, okay, let me erase this. If this angle is equal to this angle, okay, if the angle EDF, okay, EDF, this angle is equal to EGF, EGF, this angle. If the two angles are equal, therefore, this is a cyclic quadrilateral. You can also use this side, okay? Using the side FG, you have to prove that this angle is equal to this angle, okay? The two angles are subtended by the same side or the same chord if you have a circle drawn around touching all four corners. Using this side or this chord, you have to prove that this angle is equal to, okay, this angle. Okay, so this angle, if this angle is equal to this angle, okay, if the angle FEG is equal to FDG, if the two angles are equal to each other, therefore this is a cyclic quadrilateral. You can also use this side, okay, using the side DG. Now, using this side, now you are going to prove that this angle is equal to this angle, okay? So, this angle and this angle, okay? Let me erase this. If the two angles are equal, then this is a cyclic quadrilateral, okay? If DEG, this angle, and DFG, this angle, if the two angles are equal, therefore, this is a cyclic quadrilateral, okay? So, you just have to prove that one pair of angles are equal, okay? Just one pair, okay? Some quadrilaterals that are cyclic quadrilaterals. A square is a cyclic quadrilateral if you have a square, opposite angles, okay? Opposite angles. If their sum is equal to 180 degrees, okay, this is 90 plus 90, okay? The angle A plus the angle C, you're going to have 180 degrees. Or you can use this angle plus this angle because they are also opposite angles, okay? Angle B plus angle D is equal to 180 degrees. So, a square is a cyclic quadrilateral. It means a circle can be drawn around this square in such a way that all four corners are going to be touched. Okay, you can see that. Let me show you. Can you see? You can draw a circle. All four vertices are touched. So this is a cyclic quadrilateral. And we have a rectangle. A rectangle is also a cyclic quadrilateral. Okay? When you have a rectangle, so angle A plus angle C, this is equal to 180 degrees. Or you can use angle B plus angle D. Okay? The angle B plus the angle D, this is equal to 180 degrees. Okay? So a rectangle is a cyclic quadrilateral. We have proved a circle can be drawn around the rectangle such that all four corners are going to be touched, okay? And we also have a right kite, okay? A right kite is a cyclic quadrilateral, okay? in a right kite, you have a pair of right angles opposite to the longer diagonal. Okay, the longer diagonal, you have it from there. Okay, this is the longer diagonal. So in a right kite, you have a pair of right angles opposite to the longer diagonal. Okay, you have a pair of right angles opposite to the longer diagonal. So the angle A plus the angle C, the angle A plus the angle C is equal to 180 degrees. Okay, automatically the angle B plus the angle D is also going to be 180 degrees. Okay, 180 plus 180, you have 360, which is the sum of all interior angles in a quadrilateral. And we also have an isosceles trapezium. Okay, an isosceles trapezium is a cyclic quadrilateral. Okay, not a scalene trapezium, not a right trapezium, but an isosceles trapezium. Okay, you have it. You can see a circle can be drawn around an isosceles trapezium in such a way that all four corners are going to be touched. Okay, so these upper base angles are equal to each other and the lower base angles are equal to each other. Automatically, the opposite angles, their sum, you're going to have 180. Okay, the angle A plus the angle C, you're going to have 180 degrees. Or the angle B plus the angle D, you're going to have 180 degrees. Okay. Okay, now let's solve a problem. Okay, you are given this problem. In the diagram below, WXYZ is a trapezium with XY parallel to UV parallel to WZ. The angle V3 is equal to the angle V4. Now, show that WXYZ is a cyclic quadrilateral. You can use the three ways to prove that a quadrilateral is cyclic. Which one is going to work for this situation? Okay, the first one says if you have the sum of the opposite angles equal to 180 degrees, then you have a cyclic quadrilateral, but we don't have the values. Or the second one says when you have an exterior angle equal to the interior opposite angle, then you have a cyclic quadrilateral. But in this situation, you don't have an exterior angle. The third one says if you have angles in the same segment subtended by the same chord or the same arc equal to each other, then you have a cyclic quadrilateral. So we are going to use the third one, okay, because you can see you have lines across this quadrilateral, okay. So you have your bow tie or butterfly shape. Can you see? Okay, we can use the third one, okay. So we are going to use this side. The simplest is to use this side, okay. If we use this side, then we have to prove that this angle is equal to this angle. If the two angles are equal to each other, then this is a cyclic quadrilateral. Okay, so let me erase this. You can see the angle x1 is equal to the angle v4. Okay, you have parallel lines, you have corresponding angles, you have F shape. Okay, can you see? F shape. F shape. Okay, let me show you. This line is parallel to this line. So this angle is equal to this angle because this line is parallel to this line. You have corresponding angles. Okay, so the angle x1 is equal to the angle v4. The reason is corresponding angles xy parallel to uv. Okay, and you can also see you have this line parallel to this line. Okay, let me show you. You have the F shape. This line is parallel to this line. So this angle is equal to this angle. Corresponding angles. Okay, you have the F shape. So the angle W2 is equal to the angle V3. Okay, the reason is corresponding angles UV parallel to WZ. Okay, corresponding angles. You have the F shape. Please check my other video in which I explained this. Okay, let's carry on. Now, you are given another piece of information. The angle V3 is equal to the angle V4. This is given. Okay, you are given. So, can you see the angle x1 is equal to the angle V4 and the angle W2 is equal to the angle V3. The two angles are equal to each other. Automatically, the angle x1 is equal to the angle W2. Okay? Automatically, because the two angles are equal to each other. So, you have proved that. Let me show you this again. This angle is equal to this angle. Okay? x1 is equal to W2. Okay? You have proved. So, because you have proved that this angle is equal to this angle, therefore, WXYZ is a cyclic quadrilateral. Okay? You have proved. So, the reason for this, you are going to say converse angles in the same segment. Converse means the reverse. Okay? You are using angles to prove a cyclic quadrilateral. If you have a cyclic quadrilateral and you are trying to find another angle, you are going to say angles in the same segment simply. Okay, let's move on. Okay, a bonus. How to find the area of any cyclic quadrilateral. Okay, find the area of the following quadrilateral to two decimal places. Okay, you are given this. This is a quadrilateral. A is equal to 6. Okay, B is equal to 7.5. C is equal to 5. D is equal to 5.5 units. Okay, you have the sides of the quadrilateral. Now, solution, we are going to find the area of this quadrilateral. Okay, this is a cyclic quadrilateral because this circle passes through all of its vertices. You can see the circle passes through all of its vertices. So you can conclude that this is a cyclic quadrilateral because the circle passes through all of its vertices. So the following formula can be used when you have a cyclic quadrilateral. Okay, you can use the following formula when you have a cyclic quadrilateral. Okay, so S is the semi-perimeter. Okay, now let's find S first. The semi-perimeter is half the perimeter. So S is equal to, you are going to multiply by 1 over 2. In bracket, you have 6 plus 7.5 plus 5 plus 5.5. Okay, this is the perimeter. You multiply by 1 over 2 to find the semi-perimeter. Okay, so this is equal to 6 plus 5, 11, 7.5 plus 5.5, 13. So 13 plus 11, 24. 24 times 1 over 2, 12. Okay, so the semi-perimeter is equal to 12. Okay, now the area of a cyclic quad, you are going to use this formula. You plug everything that you have into the formula. You have this. Okay, A is equal to 6, B is equal to 7.5, C is equal to 5, D is equal to 5.5, S is equal to 12. Okay, so the area is equal to, use your calculator, 35.05. Okay, 35.05 to 2 decimal places. Okay, 35.05 square units. Okay, because this is the area. Okay, so you can find the area of a cyclic quad using this formula. Okay, you can also use the formula for the area of a cyclic quad. Okay, you can also use this formula to find the area of a square, rectangle, right kite, and isosceles trapezium, because these are cyclic quads. Okay, so we are done with 7 of 25.